Hi, and welcome back for part two of our linear programming presentation. We're looking at the scenario where we were trying to maximize the number of people served from delivering containers of water and medical kits. We had identified the objective function and the constraints, and we had used Wolfram Alpha here to get this graph of our feasible region. And just to recap, the value of x and y that will maximize and minimize the objective function must come from the vertices of this feasible region. So now we're going to begin the task of finding the vertices here. So looking at the vertices, or looking at the graph, we can see some of the vertices just by looking. I'm going to toggle back to see the ones that we have identified here in this slide. So this is the ordered pair 0, 0, this vertex here. If we travel down the x-axis, this is the ordered pair 3000, 0. And if we look at this vertex here, we can see that it is the ordered pair 0 on the x-axis and 6000 on the y-axis. So we actually know 3 of the 4 vertices just by examining the graph. That's pretty fortunate. To find the 4th vertex, the one missing vertex, we need to take note of what intersection of lines it comes from. And so in this case, it comes from the intersection of our inequalities. If we think of them as equations, x plus y equals 6,000 and 20x plus 8y equals 60,000. Okay, we're thinking of them as equations now because we are wanting to find where the two lines cross, okay, where those two equations have common solutions. And so we are going to treat them as equations for a moment here. We can solve this system of linear equations either by graphing or using the method of substitution. And in this case, we'll use the method of substitution. So first, we'll isolate y. In this first equation, we'll call it 6,000 minus x. And now we have two names for y. We'll substitute this alternate name for y into the second equation. So we have 20x plus 8y, but again, we're using a y's other name. And that should be equal to 60,000. Continuing on with our method of substitution, we have 20x plus 8 times the quantity 6,000 minus x equals 60,000. And that is an equation that only has a single variable. And so we can go through our methods of solving linear equations to solve this. When we do that, we end up with a solution x equals 1,000. So now we know that this vertex would be representing 1,000 containers of water, since x is representing containers of water. And we just need to find the y value that goes along with it. To find that y value, we'll plug in 1,000 into our equation y equals 6,000 minus x. And of course, that means that we need 5,000 medical kits, or y is 5,000. So our 4th vertex then is the ordered pair 1,000, 5,000. So now we've identified all of the vertices of our feasible region. And again, with linear programming problems, the vertices produce both the minimum and the maximum. In this problem, we're wanting to maximize the number of people helped, so we're looking for the maximum. To figure out which vertice will maximize P, we're going to plug those values for X and Y into our function that gives us the number of people served. Well, if you bring no containers of water and no medical kits, you will serve no one, right? No one, at least not with your water and medical kits. If you bring no containers of water and 6,000 medical kits, then you're going to serve 36,000 people. If you bring 3,000 containers of water and no medical kits, then you're going to serve 30,000 people. If you bring 1,000 containers of water and 5,000 medical kits, you'll serve 40,000 people. These calculations, we see that 40,000 is the highest. And so that's going to tell us that we can serve 40,000 people at most. That's our maximum. And that will happen if we stock the aircraft with 1,000 containers of water and 5,000 medical kits.